Hey everyone, welcome back to the channel. In today's video, we're going to be going over limits and continuity of functions. By the end of this video, you'll understand the strategy to evaluate limits, as well as evaluate whether a function is continuous or not. And we'll be going over multiple example problems to practice the concepts we've learned. If you guys find this video helpful, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. Alright, let's get started. Alright, so as we've been going through kind of the introduction to calculus, we've talked about limits and we talked about the slope of a tangent line and taking the limit as h goes to 0. But what does that actually mean? Well, what it's saying is we're going to get very close to the value that it's approaching, but not actually become that value. So a limit is, if we looked at a function that had maybe a vertical asymptote, so say we had a rational function like this, where one of the lines here was like that. We could take the limit, and this goes up and on forever, where this blue line here is a vertical asymptote, so we could put like that. And what we're saying is, as x goes to 0, what is happening to y? We're kind of looking at like the end behavior here. So as x goes to 0, this is going to go to positive infinity. So that's really what a limit is saying. It's getting very close to, but never actually touching that number. So here, we're going to get very close to 0, but we're never actually going to touch 0, and our value will just be positive infinity. It's going to go on forever. Now, to look at an example, that's kind of like a graphical answer to our question of limits. But if we looked at it algebraically, what we can do is, for polynomial functions especially, we can just plug in the limit as x goes to 2. So in this case, we would just plug in x is equal to 2. So this would be x squared is 2, so it's going to be 2 squared, which is 4. So it'll be 12 plus, and then x is 2 again, this is 8, minus 1. So we're going to get 19. That would be the limit evaluation of this function here. As the limit approaches x equal to 2, the function will be around 19. Now, that's a big note to... Now, that's actually one of the strategies we use to evaluate limits. We just plug it in. It's kind of the direct substitution method. And for polynomial functions, and again, a polynomial function is the form of this expression here. And it looks kind of complicated, but basically it's saying coefficient times a variable, so like x to the power of 5, x to the power of 6, doesn't really matter. But the n term, so the degree term, so that x to the power of 6 needs to be positive, and they need to be integers. So we can't have, this is not a polynomial function. That would not be a polynomial function, because it's a negative power here, or negative degree. This would also not be a polynomial function, because this is not an integer. This is a fraction, this is 0.5. So integers are whole numbers, so that's very important to note. And for these polynomial functions, what we can say is, as x approaches a of a function, it's going to equal f of a. So again, just subbing in that x value. Now, before we kind of solve some problems, I want to go over the strategies to evaluate limits. So we have direct substitution. That's what we did in the last example there, where we just plug in the x value. We also have factoring, so that's when we factor the numerator and denominator. We have rationalizing, so that's when there's a radical or square root, and we need to get rid of that square root. And we have one-sided limits, so approaching from the left or approaching from the right, and change of variables. So this is kind of indirect substitution, and we'll do an example problem of that. Okay, so we have a number of example problems where we'll go over all these strategies. So for this one, this is going to be a direct substitution method. So we're going to say 3, and we're just going to plug in this x value of 2. So 3 times 2, and this is 2 squared plus 2. So on top, it's going to be 6, and on the bottom, it's going to be 6, so this limit evaluates to 1. And that's, again, direct substitution. Next, we have this limit as x approaches 2. So if we were to try the direct substitution, and again, it's not wrong to try it, but you'll see why it doesn't work. So if I were to plug this value in, well, on top I'd get 4 minus, well, 2 squared is going to be 4, so that would be 0. And that's over 2 minus 2. Well, this is going to be, if I write 2 minus 2, this is going to be evaluating to be 0 over 0. This is an indeterminate form. So we actually can't do that, because that's not what this limit is actually going to be. What we have to do is we have to solve this limit by factoring. So up top, this is actually a difference of squares. So 4 is a perfect square, and x squared is a perfect square. So I can write that out as 2 minus x, and then 2 plus x. That is the difference of squares. Again, we have a squared minus b squared. That evaluates to a minus b times a plus b. Now, if we take, again, the limit as x goes to 2, in the bottom we also have 2 minus x. So what we can do here is we can cancel these. And once we've canceled them, now we've kind of removed that indeterminate form. So here we can now evaluate and plug in x is equal to 2 to this part of the expression. So the limit as x goes to 2 of this function will be 2 plus 2, and that's going to equal 4. So that would be the solution to part B. Question C here, we have the limit as x approaches this, x approaches 0 of this function, and this is going to be an example of where we rationalize. And rationalize is basically kind of removing the radical or solving the radical, like rationalize the numerator or rationalizing the denominator. So here, what we're actually going to do is we're going to transform this function by multiplying by its conjugate. And what a conjugate means is the same term here, but we're just going to change this to be a positive. But if we do that, what we're going to have to do is do that, if we're going to do that to the numerator, we have to do it to the denominator as well. So I'm going to multiply by the conjugate. This is root 7 minus x, and it's going to be plus root 7 plus x. And now this is going to be the same thing on the bottom. And the reason we do this is because we can't just change this expression. We have to multiply the numerator and denominator. We've effectively just multiplied it by 1 right here, and then we can cancel. Or then this expression is going to be changed. So when we do this, you can also see that this is actually a difference of squares. So this is a minus b, now times this red part, which is going to be a plus b. So we already know what that equals, and it's going to be a squared minus b squared. So a squared, or this value squared, is just going to be 7 minus x. And then it's going to be minus, and I'll put in brackets, the b value. So this is going to be 7 plus x. And this will all be over x, and then times, I'll do in brackets, 7 minus x square root plus root 7 plus x. And of course, we're trying to evaluate this limit. We're just kind of playing around with the math of the function right now. Now, what's going to happen is if we evaluate this, this will be 7 minus 7, so that's going to be a minus, so that will cancel. And it'll be negative x minus x. So this is going to be negative 2x divided by x, put a bracket there. This is 7 minus x plus 7 plus x, all under square roots. And at this point, we can now evaluate this and cancel those out. This is similar to when we were solving for the instantaneous rate of change or the slope in the previous videos. But the reason we couldn't just do direct substitution here is if we subbed in 0 to this value, then we have divided by 0, so we'd be undefined at that point. But now, by doing this kind of manipulation or multiplying by the conjugate, we can actually now sub in this value. So again, we're still taking the limit as x goes to 0. This is going to be negative 2 divided by, and it's this term here. So we're going to have 7, so it's going to be root 7 minus 0, so that's just going to be 7, plus root 7 plus 0, so that's root 7 again. We'll now get negative 2 over 2 root 7, and this evaluates 2. These 2's can cancel here. This will turn into negative 1 over root 7. That would be the limit of this function as x approaches 0. So now for part D, we have a method where we're going to use indirect substitution or change of variable kind of limit evaluation. So what I'm going to say here is, again, if I plug in this x to the power, or sorry, x is equal to 27, that's going to be 27 minus 27. So that's going to be 0. So we can't do that. But what we can do is I could say u is equal to, I'm making a new variable, I'm going to say u is equal to x 1 over 3, to the power of 1 over 3. So I'm basically saying u is equal to this term right here. Then if I rewrite this function, it's going to be u minus 3, right, because that was a value of u. And then x, well, to get x to the power of 1 over 3 to just be x to the power of 1, we have to multiply it by, or put it to the power of 3. So this is going to be u cubed here, minus 27. Now the limit, if we change the x variable to this new value here, we have to change what the new variable is approaching. So I couldn't write u to as going to 27. That's not correct. What I have to write is u, and then, okay, well, what is x? Well, x is 27, or u is 27 to the power of 1 over 3. So this value will just be 3. Now this is going to be correct. So I've changed the variables in the function itself, and I've also changed the variables in the limit evaluation, so where x is approaching. So now we're going to use a bit of factoring here as well, because here we have a difference of cubes. So if I rewrite this, I'm going to say, or sorry, u as it goes to 3, not x. So u as it goes to 3 is u minus 3. Now this difference of cubes is going to be a cubed minus b cubed, and that's all going to equal a minus b multiplied by a squared plus ab plus b squared. So I'm going to use this form and apply it to this difference of squares here. So this will end up being u minus 3, and then now it'll be u squared plus 3u, and then plus 9. Because in this case, our b term is 3, and our a term is u. So we just plug that in wherever we see it. Now, what we can do here is we can cancel this top and this bottom here. So now we'll have limit as u goes to 3, and it's going to be 1 over u squared plus 3u plus 9. Here is when we can now evaluate this. We can now plug in this u value of 3 to this function. If we did it before we canceled this, u minus 3, that would be 3 minus 3 here. That would be 0 in the denominator again, and we can't do that. So what's going to happen is we'll have 1 over, and this would be 3 squared, so u is going to 3, so 9 plus 3 times 3, also 9, and then plus 9. So the limit as u goes to 3 is going to equal 1 over 27. And that would be our answer right there. So now that we've talked a little bit of limits and we've gone through some example problems, I want to talk about limits that exist and don't exist. Previously, we've just been evaluating limits that do exist, but there's going to be situations where they don't exist. So in this case, we have to look at the left side and the right side of a limit. And what that means is the left side is limit as x goes to 5 from the left. So that's basically saying we're going to go to 5 from values to the left of 5. So we're going to be like 4.99999. That would be a value just to the left of 5. In that case, this limit, if we look at this function in the graphical sense, that would be negative infinity, right? Because this is going to go from the left side, it's going to go all the way to negative infinity as it approaches this vertical asymptote. So that would be fine. Now if we look at the other side of it, so we're looking at the positive, so from the right, this is what from the right means. We're going from the right side of this vertical asymptote and approaching it. Well, that's actually going to be positive infinity. As you see, as we go closer to 5 from this side, so that's when we're going to be like 5.00001, so very close to 5, and from the right side of it. Well, that's going to be positive infinity. And what you can see here is the left side of the limit, so this negative value approaching 5 from the left, does not equal the right side of the limit, or approaching 5 from the right. So we see that negative infinity, positive infinity. If that's the case, we know that the limit as x goes to 5, since they don't match, so now we're not actually looking from the left or the right, we're just saying what's the limit when x goes to 5. We would say this does not exist, DNE, because this one does not match this one. So if the left side of the limit doesn't match the right side of the limit, then the limit at that number will not exist. So now we know when a limit is defined, and that's really important for continuity, and that was kind of the predecessor step for continuity. So here, a continuous function is continuous if f of a is defined, so f of the value we're looking for is defined, and then the limit of f of x exists, so x as it goes to a, and the way we check that is we say the limit of x goes to a from the left equals the limit as x goes to a from the right. So in the previous example, that was not the case, right? We had a negative infinity and a positive infinity. So that means that the limit at that value does not exist. So that's how we check to see if that limit exists. And once we know if it does exist, then that checks one box of the continuity box to see if this function is continuous. And we also have this third step here. The third step is going to be the limit of f of x as x goes to a equals f of a. So the value of that limit, or the value of that x value. So now we can start asking questions on, is this function continuous? So we look at this box here, this graph here. What we'd say is, well, let's look at the first criteria. F of a is defined. So f of 1, so that's our a value is 1 here. We're saying, well, that is defined because there's a dot here. So it checks that box. And then it says, the limit of f of x exists. So that's saying, okay, if we get really close to a is equal to 1 from the left, so like a is equal to 0.999, and the limit from the right, so a is equal to like 1.001, if those two equal, then it exists. In this case, this function the limit would exist at that value. They would be the same, so we know the limit exists. So this value is checked off. So this function is looking fairly continuous, or almost continuous, but we need to satisfy this criteria here. And if we look at it, the limit of f of x is x to the power, or as it goes to a, that equals f of a. So the limit here, if we look at the limit as x approaches a, that's going to give us a value of 4, right? That's like the limit from the left and the right. That would be a y value of 4 right there. So that's our value, and we have to see if it matches the function of f of a. But we see here, this is the whole. So the function of f at 1, which is a, is equal to 2. So that doesn't match the actual limit value, which is 4. So it does not satisfy this, and so we would say that no, this function is not continuous. I've rewritten now the continuous function criteria that we need to meet, and we're going to ask again, is this function continuous? So in this case, let's look at the f of a. Is f of a defined? F at 2. So if we look at f at 2, well, this represents a vertical asymptote, right? X is equal to 2 represents a vertical asymptote. And what a vertical asymptote means is that we're going to get very close to this value but never actually touch it. So I already know that this thing, this f of a is defined, is not true because there's a vertical asymptote. The function never exists at x is equal to 2. So we now know the function is not continuous, but let's go through the other criteria just so we get familiar with it. The limit of f of x as x approaches a exists. So that means that we need to check the limit of x going to a from the left, so this negative value, equals the limit as x approaches a from the right. So if that's the case, then we know the limit does exist. Let's look at this. The limit as x approaches a, and in this case, a is equal to 2, from the left, well, it's going down. So it's going from the left side of the vertical asymptote, so it's going to be negative infinity here. Now, if we look at from the right, the limit as x or a goes to 2 from the right, like 2.00001, that would be positive infinity, right? Because we're going this way now. So now again, this is where a situation where this does not exist because the limit from the left side of the value does not equal the limit from the right side of the value. And lastly, like we already know, this function is not continuous, but if we look at this last value, the limit as x goes to a of f of x, so the limit, well, again, we can't really evaluate this criteria because this doesn't exist. There is no limit. We already said that it does not exist. So we don't really have a value that's showing what that is. And then it equals f of a, and we also know that this is not defined, so we can't even find that value. So this third step is kind of built on the first two, and so if the first two are gone, you can't really evaluate the third step. But again, we just want to say that this function here is not continuous, f of a is not defined, and the limit as x goes to a does not exist. Okay, so now we're on to the last problem here, and we're saying again, continuous function, is this a continuous function here? We have our criteria on the left here, and we're trying to see if we can say for certain that this is a continuous function. So f of a is defined. Let's say a is this c1 value. So we're evaluating this c1 here. We have this dot, and clearly this function goes through that dot. So in this case, a is equal to c1. So that is continuous at c1 because it's defined there for the first criteria. Now the limit of the function as x goes to c1. So we have to check the limit as x goes to c1 from the left and make sure that's equal to the limit of c2 from the right. So that's going to be a positive there. Now if we look at that, when we get really close to here, we're going to get a value of close to m, right? From the left side. And then also when we go from the right, it's also going to be a value of m when we go from like c1.000 whatever. So now we can say that this limit does exist because the left side equaled the right side. So the left side of the limit, where values were just under c1, equaled the right side of the limit, where values were just higher than c1. So that works. Now the last step here, we have f of a, like the limit as x goes to a of the function, equals the value at that x value. So here, we're going to say that, well, as we get close to m, so we have a limit here, and this value would be m. And now if we plug in f of a, which is c1, so we're plugging in f, the function, at c1, what value would we get? Well, we'd get this value of m here. So this actually checks out as well. We said that the limit does exist, and the limit at that value would be m, because it goes to the left and the right, it approaches this value of m. And the function is defined and is given a value at that x variable equal to the m value again. So this third criteria matches, And we can now finally say that this function is continuous, so yes. Alright, so I hope you found this video helpful. If you did, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. If you have any thoughts on what you want me to cover next, let me know down in the comments below. I do weekly videos on math and physics tutorials, as well as how to improve the learning skills and the mindset of students. Thanks for watching, and I'll see you guys in the next video.